My name is Haojin, and I feel great honor to present our security study about Electron apps and the programming methodology to tame DOM functionalities. This is a joint work between Microsoft Research, where I'm an intern, and Tsinghua University, where I'm a PhD student. Here is an outline of this talk. I'll start from some background on Electron apps and payload injection bugs, followed by an empirical study of existing Electron apps. I'll then introduce our methodology, which aims to solve the security problems we found in the empirical study. And finally, I'll present our evaluation results. So Electron is an emerging platform for desktop apps. It allows developers to build cross-platform desktop apps with JavaScript, HTML, and CSS. Popular Electron apps include Visual Studio Code, Microsoft Teams like GitHub Desktop, Figma, Dropbox, Twitch, and so on. And that's some background on payload injection bugs. This is what we are targeting in this study. It should be a very familiar concept to you. Think about secure injection like this. So the text in red is the injection payload, escapes from its intended scope, that is string enclosed in a pair of double quotes and turned into a code that is the where clause of its secure statement. So in web programming, payload injection tags include process scripting and scriptless tags like a CSS injection. Electron apps inherit this problem from web apps and usually have a wider attack surface due to the interaction with local files and other protocols like Circle, like SSH, etc. And there is an unclear security boundary because those local files and inputs from other protocols all fall into a single origin, that is a file origin. They are not easily separated into, say, https://a.com or b.com. Therefore, they are not protected by the same origin policy. And thanks to Electron's capability to access local file system network, an injection attack here is usually more damaging than process scripting on a web page, since here, attacker can access your local machine. Now I'll discuss our empirical study of Electron apps. The first case is Microsoft Teams, a business communication platform. The main functionality is instant messaging, including group chat and private messages. We look into how Microsoft Teams sanitizes a chat message and found it's a very difficult task. So first, before a message is sent, it is sanitized by a clean site sanitizer. And after that, the message is rendered instantly on the sender side and sent to the server where it is sanitized again. Server-side sanitizer is independently developed in a different language that is C#. The sanitization rules are similar to the client-side sanitizer with some very slight differences. Then, when the message reaches the receiving client, which can be many clients in a group chat, it is sanitized again one more time by the client-side sanitizer before it's being displayed. And the sanitization logic includes very complicated rules. I just name a few here from Microsoft Teams client-side sanitizer. So first, it needs to rewrite external resource URLs, rewrite a target attribute, a rel attribute, and also need to filter out special characters considering all forms of the encodings. Here is an example showing 5 ways to encode a left curly bracket, which are all filtered out by the sanitizer. And for CSS, it needs to remove URL and attribute functions, position fixed declarations, comments, and CSS properties, then null invite list containing hundreds of CSS properties. Remember, this is an incomplete list. The sanitization rules in Microsoft Teams are in fact much more than this. Although Microsoft Teams sanitizers consider so many corner cases, we still found a way to bypass them, allowing an attacker to leak users' IP addresses and activity buttons and fake chat messages by sending a malicious message to any private chat or group chat. The first vulnerability allows an external image to be loaded using a carefully crafted inline CSS, like this. First, we need to break the URL into 2 parts using a CSS comments so it won't be filtered by both the client and server-side sanitizer. Since the server-side sanitizer rejects any HTML that triggers the syntax error, the UR comment XL thing would trigger syntax error ICCS property value, but here this enclosed inside quotes and parse that value of test1. The clean-side sanitizer simply split the string with semicolon to filter out unknown CSS properties without recognizing single or double quotes. So here test1 and test2 are split and then removed. And the clean-side sanitizer then removes CSS comments, so the X comment is removed, leaving a fully functional URL function in the CSS. This allows a tracker image to be loaded from the attacker server, leaking users' IP addresses and activity patterns. The second vulnerability allows an opaque overlay to be created covering up the actual chat messages. So Tames on the client side includes a message post-processing module used to render interactive contents. The module runs after the sanitizer, runs all the sanitizer after all the server-side and client-side sanitizer finish their processing. So it's not restricted or sanitized by the client-side sanitizer. It first searches for HTML elements like this and applies certain transformation. Here, assigning its value attribute to its class attributes. With the message post-processing model's help, an attacker can construct an element with a class attribute, which is clearly disallowed by both sanitizers. Using some built-in class in Tames whose CSS includes position fix and then set to 0, which again are disallowed by the sanitizers. An attacker can create an overlay and put fake messages in it because the post-processing model actually runs after all the sanitizers. Now, combining these two techniques, an attacker can fake chat messages and leak the user's IP addresses and activity patterns. And other apps in our empirical study include Visual Studio Code, which also has a markdown injection bug caused by a flaw in state machine-based URL extractor. And full cross-site scripting that is beyond the CSS or markdown injection is pretty common in Electron apps. We found Grasshopper, a SSH client, extracts file paths from terminal output using a regular expression like this, and considers them safe to display, that is, safe to add to the DOM tree. But this cross-site scripting payload matches that regular expression and will be treated as a file path in Grasshopper. And we found many app developers just don't recognize the possibility of an injection attack. We found their apps come with no sanitization logic and directly interpreting user input as HTML. A semi-automatic scan exposed certain vulnerable apps out of a dataset of 70, which we manually confirmed them. So after going through all those sanitization errors, now I will introduce our methodology, which is named DOM tree tab. So the current situation is, we find app programmers are required to expect all the unexpected, including unexpected input from unexpected source, flowing through unexpected paths, and specify those unexpected situations as sanitization rules. And also, I need to find the right place to invoke sanitizer so it does not miss some data passes. Our perspective is, we let the app programmers specify their intentions rather than their non-intentions. That is, what the DOM tree should be like. And tab is a well-known mechanism to specify a programmer's intentions. We give further explanation in the next slide. And we also borrow an idea from the programming language community, that is, types of data. So the basic idea is to use sample values in JSON or XML format to construct a type or otherwise untyped string object that captures the programmer's intentions of the object and can be used for type safety. So after discussing those tools, now I'll explain how our system works. The programmer first tests his or her app's functionalities. In the meantime, our tab builder monitors DOM tree and generates a DOM tree tab. The DOM tree tab grows as the programmer covers more functionalities of his or her app. And when the DOM tree tab no longer grows, we say the DOM tree tab converts not the programmer packages into the release. The programmer sometimes needs to make a few adjustments to help the DOM tree tab converge, which we'll cover in a later slide. And on the user side, our tab enforcer model, built into the Electron runtime, monitors every mutation to the DOM tree and checks it against the DOM tree tab, and stops every unexpected DOM tree mutation. And both tab builder and tab enforcer depend on a DOM interceptor module, which is implemented inside Chromium and involves a set of hooks within Blink, that is Chromium's HTML engine, which I'll explain in a later slide. Now I will give an example of how tab builder constructs a DOM tree tab from an actual test run. On the left, here is a DOM tree, standard head and body element, 2 divs inside its body, a list and some images. On the right, it is what tab builder would extract from DOM tree. You can see some attributes, like the full attribute is removed. We see the 2 li elements are merged into 1. We see the on-click attribute is converted to JavaScript tokens, and we see that the image elements are also merged. Note that the CSS styles are in fact captured by the DOM tree tab. We have detailed explanation in the paper, and also we omit the content of the script element, which the explanation is also left to the paper. Now, suppose some functionality of the app modifies the sidebar div to this. So we'll generalize the DOM tree tab. In other words, invert the new version of sidebar div element by adding parts green, that is one UL element with ID Z5 and containing an IR element, and one new value for the existing image element, and also a new image element because the ID is previously different. And after obtaining a DOM tree tab that combines the existing one and the changes, the programmer can also manually adjust the DOM tree tab if the automatically constructed version does not exactly capture his or her intentions, using attribute value wildcarding and subtree flattening, which are detailed in the paper. And there are a few implementation details. We need to ensure we can read these and potentially stop every DOM tree mutation. And we found 5 choke points in Chromium's DOM tree mutation code passes and added hook functions there. And when there is a wrong assumption in some related work that only elements connected to the DOM tree can make persistent effects, like triggering an HTTP request or executing JavaScript. But in fact, there are situations, either transient or sometimes even persistent, where elements can become disconnected from the DOM tree, but they still make persistent effects, HTTP requests, or JavaScript execution, which would be otherwise evading our DOM tree tab checking, since they are not even a part of the DOM tree. Our approach to this is to defer their persistent effects until they are connected, available for tab checking. We evaluated the practicality and security by applying it to 18 vulnerable apps we found in the empirical study. For each app, on top of the DOM tree tab constructed by tab builder, we only needed to make a few manual adjustments or no adjustment at all and catch every attack we found as tab violation. We also tested on 6 Visual Studio Code extensions to see if our methodology is suitable for large apps with an extension ecosystem. And for performance, we use Speedometer 2 for the performance benchmark. We found the performance overhead should be negligible under a realistic workload. That is, when the simulated user actions are fired at a frequency of 10 per second, and the slowdown rate only reaches 26% at 100 actions per second, which is unrealistic for a human user. So to conclude this talk, we did a study of real-world Electron apps. We found payload injection bugs are prevalent. We see there are inherent difficulties in the sanitization approach, that is, to expect all the unexpected. Our methodology is to let app programmers specify their intentions for the DOM tree as opposed to their non-intentions for input streams. We catch the programmer's intentions from test runs, and we safeguard the app on the user side with runtime tab enforcement for the DOM tree, and the result is we can prevent injection bugs in Electron apps with pretty low manual efforts and performance overhead. So, okay, that's all. Do you have any questions?
Thank you for the talk. I think this is a very smart methodology for the defense. But I have a question on the practical side here. So how do you imagine that the developers will be willing to adopt this methodology? Because it looks like that they'll need to manually add the type tags to every DOM element that they want to defend. And this is, like you mentioned, also a human factor that could potentially be problematic.
Yeah. Thanks for that question. Let me clarify this. So, in fact, we primarily rely on an automatic generation of the DOM tree tab. That is, we record what the DOM tree should be like from test runs and generate the DOM tree tab. We only need a very few manual adjustments, which is shown in this slide. That is maybe within 10 manual adjustments. So primarily, we rely on the automatic generator for DOM tree tab that only needs the developer to test every feature of its tab. So I believe the efforts to apply DOM tree tab should be much smaller than writing the sanitization rules in, say, Microsoft Teams, which we find tens of sanitization rules and 2 sanitizers.
Great, thank you.
So I have a quick one. In your slides, you explained the example with the widening of the URL parameter where you had one instance with foo.com and the other one with bar.com. Is that something that would have to occur for every message that is sent? So for every URL that ever appears in a message, or is this just a static and gets widened to any allowable URL?
Sorry, which page? You mean the imperial study or the...
I think it was where you were going through the individual steps of refining the type. Yep, right after this.
Here.
So here you have foo.bar, and the next slide you have, or foo.com, here you have bar.com, and then you have the or operator there. Is that something that would have to happen for every message? Or is that just static for the application, and then at the end of the day, you accept any URL anyways?
So our assumption is that many of those places where an external resource is required should only expect a whitelist of backend URLs, or backend servers. So I believe from some test runs, we can already capture the legitimate backend origins, like here, maybe foo.com and bar.com. But if in some of the apps, they need to accept any backend origin here, then we need to let the app programmer use the attribute value varcoding, that is, put a star here so that it can accept any backend origin.
Okay, thank you.